Today we have David Rydh from KTH speaking on the existence of topological modulus.
So thanks very much for being invited to speak here. And we have seen many talks today about using existence theorem for good moduli space. I want to go to topological moduli spaces, and it kind of hinted in Michele's talk. And I'll try to stick to two aberrations this talk, and it's good moduli spaces and topological moduli spaces. So here we have seen that there is this existence theorem due to Gerhard Doper, Jochen Heinoth, somewhere here, and Daniel Happeleisner, also somewhere here, I think. Yeah, I see Jochen at least. And the nice thing about this existence theorem is that it's in terms of something very resembling the valid criterion of properness. There is this theta stack, and there is this ST bar stack. And what I'm going to do today is a non-validative existence theorem for topological moduli spaces. And the reason for doing this weaker result in some sense, because it's not really applicable in most situations, is that there is something in between here, which is non-reductive moduli spaces. And as Vicky said in the beginning of this conference, this program that's been running on the spring has really been motivated by non-reductive GIT. And so there's lots of nice things happening here. What's missing here is really a validative existence theorem. So if you would like, for example, doing this moduli space of AR stable curves, when you also allow these special cases where you have non-reductive stabilizers, if you want to verify it, you really would like to have something similar to this one. But the upshot is that there exists something at least on this one. And I would like also to, I think this sheds some light over the whole picture. So let's just start with good moduli spaces, and I'm going to repeat the definition just to compare with the topological definition, and also to highlight that there's some homological thing going on. So the definition is not going to be important, but illustrative. So this is a good moduli space. So now always EMS. If this map should be quasi-compact, quasi-separated. This is just so that we can talk about push forward of coarse-grained sheaves. And we want this, the push forward of coarse-grained sheaves is by definition a good moduli space exact. So not just left exact, but also right exact. And then finally, we require that the global sections of OX, or the structure sheaf of OX, is the push forward of the structure sheaf of the stack. So it's a homological condition. And it's amazingly useful. So there's also so this is something capturing GIT in characteristic 0. There is also a characteristic P version called adequate moduli spaces. There one is still in some kind of homological flavor, but it also involves algebra, so it's perhaps less homological. In a non-reductive situation, there is also similar weaker exactness conditions, so it's also kind of homological in nature. This won't be. And the examples, you have all seen, it's affine GIT, so, but we have to take a linear reductive group G acting on some affine scheme. Then we get an, let's call that X, and my stack is the spec A mod G, and the good moduli space is the invariant ring. So my blackboard bold will be moduli spaces and curl will be stacks. And the reason here is simply that exactness is just saying that taking G invariance is exact, which it is for linear inductive groups. And there's also projected GIT. So G is above acting on, let's say, a projective polarized scheme, and then we get the semi-stable locus on G to the proj of the invariance, which is the GIT quotient. This is also, yeah, sorry, put moduli spaces. And I mean, I want to state the existence theorem. We already saw theta appearing in Jochen's talk and in Michele's talk. Perhaps I should give a proper definition or example. So my theta r will be spec r. So the affine line over spec r mod out by gm. And here the action is only on x. And we weight 1. And the picture is the following. Well, let me press first to the good moduli space. So that's the spec of the invariant ring of this, so that's just spec R. And my picture for spec R, and now unfortunately Michele, I mean, he had the squiggly arrows for the theta generations and he had the straight arrows for the specialization. I'll do the opposite. I'm really sorry, but I have to do it. So we have the residue field, which I at least use the same notation for. I'll use capital K for the fraction field. So this is my R. So very sorry for the, I mean, he had the straight arrows. Above the special fiber, I will have the theta k, which has the, let me first call it 0 with k and 1 k, and I will, for this theta specification, I'll draw the less than equal sign. And the special fiber looks the same, and then there's this generation here. So it has 4 points, and then these are the fibers. So I guess we could. And this is the locus x equals 0. So this is just a copy spec R plus the GM. So here the action is trivial, and here this is the locus. X is not 0, and there the GMX freely. So I just get spec R. But I can also think of the vertical lines as being 2 thetas, as I've indicated here. Perhaps green. This is a theta small k, and this is the theta capital K. And as Jochen said, we should focus on points with maximal stabilizers, in this case, the 2 zeros in this scheme here. So really the action happens on points with maximal stabilizers. And I will call these points special. These are the things which are closed in their fibers. So this is the theta r. And it also has the companion as the bar r, which is really just the A2 with the weights 1 and minus 1, as Jochen, but it's a local version of that. So if I pick a, let me call it pi, or perhaps t, the uniformizer of R, so here R was the dVr, uniformizer t, fraction field small k and fraction field big K. So here GM acts by weights plus and minus 1, and then the quotient by GM. So this is another way of describing this is to take A2 with weights plus 1 and minus 1, and then just base changing this to spec R using the unit YCT. And the picture is somewhat similar. We have the generic point K, so it's also living over spec R. So this is S to bar R. But now instead we have 3 points in the special fiber, we have 2 just K points. And then we have this special point which has a GM stabilizer. And this now specializes to this. So as before, here we had 1 theta and 1 theta. Now we have 2 thetas in the special fiber. And instead we have the valuation, 2 different valuations. So in Michele's talk, he was talking about doing 2 different, I mean, this is kind of being separated, then they want to be the same. Here we are instead requiring them to specialize to some other point instead. So I think I'm now ready to state the existence theorem in some version. And I'll put simplicitly, I'll do it in character 0. So this is by Gerard, Dan, and Jochen. So take some stack of type over a field of characteristic 0, then X admits a good moduli space, a separated good moduli space. If and only if. And Michele listed 3 conditions, but the first one is actually superfluous in characteristic 0. So we just have this theta completeness and S completeness. So as Michele said, it's about filling out these diagrams. So, and to be precise, we are starting with theta for any DVR, and we're moving the unique closed points. So these are actually, these are both local stacks that come with a unique closed point. So this is a unique closed point here, and this is a unique closed point here. So I'm removing that and mapping it to the stack, and then I'm asking for the existence of a filling here. Oh yes, perhaps you should also put affine diagonal on the stack, and S complete is the same thing for S bar. And this is for all DVRs and all map stacks. But behind this is exactly what Michele listed as the first condition, that there is also this locally reductive or locally reductive. So this condition 2, S completeness, implies that stabilizers at closed points, so for all closed points, so corresponding to closed orbits, if you are in the GAT situation, the stabilizer is reductive. And since we are in factor 0, this means that the stabilizer is linear reductive. There's no difference in factor 0. And for linear reductive stabilizers, we have this local structure theorem, so saying it's locally reductive or locally linear reductive. And what this means is that I can essentially say that x locally at x is given by affine GIT. So there exists a tau map where this is some spec A, and let's just do GLAN for simplicity. So the stack is locally around every close point, just an affine GIT situation. And let me now perhaps go back here also to say that the relation here is really going to say that good moduli spaces are topological moduli spaces such that close points have, let's say, linear reductive stabilizer. So the difference here, you can measure it by how the stabilizer looks like at close points. And similarly, this non-reductive situation will also be topological moduli spaces such at the stabilizer of X acts on the tangent base in a certain way. Yeah, let me not say exactly how that is, but but at least there is a condition on the action of stabilizers on tangent spaces, which is enough to deduce that you are non-reductive good moduli space if you are a topological moduli space. And unfortunately, positive characteristic, we don't have the same result. We don't know that reductive implies this. This is I think it's published around 20. Right, I think it's time to go towards the topological side. And as I said, it's this. But what is known in positive characteristic is that if we have theta completeness, S completeness, and we are locally reductive, then it's fine. So this is not known. In positive characteristic, but we do know that theta stability, theta completeness, S completeness plus locally reductive, that there exist as separated and now not good but adequate moduli space. But the problem is finding these local structures in positive characteristic is kind of hopeless. I mean, there are Jared among others are working on this, and there's. I think it looked very gloomy a couple of years ago. Now it looks a bit more hopeful that one can actually achieve this. So now I'm just erased the definition of good moduli spaces, so let's go to the topological situation. And this is really just a small variation of the definition of a good quotient in Seshadri's, one of Seshadri's paper. So unfortunately that's called a good quotient. It's not good moduli space, but good quotients are really topological moduli spaces. So again, its terminology is not so good. And the idea is to extract the topological phenomenon that happens for good moduli spaces. So one thing that I haven't said, but let's put this in definition now. So again, I'm looking for a stack mapping to an algebraic space. This is a topological moduli space, TMS. If, again, we need just some hygiene requirements, then we need this to be universally closed. So like in Shashari, you would only assume it's closed. And then Shashari formulates this as saying that if you have two closed gene variance subsets, and if they push them forward along pi, and if they intersect, they should intersect with each other. But this is actually exactly the same as saying that there exist. So for all, I'm going to modify this a little bit soon. For all points, there exists a unique closed point, which I call x naught in the pre-image of x. And we see that this happens here. I mean, if I take this point, this is the unique closed point. This is unique closed point. This is unique closed point, and this is unique closed point. If I would have two closed points, then they would be disjoint, but the image would coincide. So by Shashari, they should have been the same. So that means that they must be close, unique closed points. And conversely, if you have this, Shashari's condition immediately follows as well. But unfortunately, just as we have to do universal close, we also have to impose this in some sort of universal way. And what we're going to do is to say that for, and now I'm going to do this ugly diagram here. So first of all, it has to be universal on x. So for any map here, I want to impose that fibers here have unique closed points. That's still kind of reasonable, right? So then, unfortunately, I also need to impose that for any finite map on the side. Now this might split up in several closed points, but if I take the Stein factorization of this map, it should have unique closed points. So the Stein factorization, I mean, usually it has connected fibers. Having unique closed points certainly guarantees that you have connected fiber. So we take the Stein factorization here. So this is my spec over x prime of push forward of the structure sheaf of curly x is. So the condition is that I want for all such diagrams and for all points now in here, there should be a unique closed point above this point. And the way you should think about topological moduli spaces and moduli spaces in general is that they are really trying to be proper. And they mean the best thing would be if there would be homomorphism to the stack and the space. It's impossible. We can't separate like 1 and 0 by a scheme, so they have to be identified. So we are forced by that. But we still want them to be as close to proper as being possible, and universal closed are, I mean, proper maps are closed, and having a unique closed point is getting close to being a homomorphism. And there's actually a different characterization of this. Let me not write it down, but it's saying that pi, this is not a good terminology, but let me just say in words. So what this means is that on a base change to any Henselian local ring, then there's a unique pre-image of the closed point, and that pair is Henselian. And if you take a proper map, I mean, it has the property that if I start with a Henselian base, then I get a Henselian along the fiber. So it's even stronger than this. And if I would have finite stabilizers, this will be exactly proper. So So it's really trying to be proper, but it cannot be because it's not separated. So let's do a few examples. So perhaps the easiest, well, perhaps example series, any germ would be, this is not over a point, it's definitely a topological moduli space. Nothing really happens when you pass to finite covers and they change. And as I said, if X has finite stabilizers, then is equivalent to having finite inertia. And well, that was a coarse moduli space with finite inertia. So we cover well-known things. It's also true that good moduli spaces are topological moduli spaces, also adequate are, and also this non-reductive are also topological. But then there are more examples, and one such is ugly beasts as P1 moduli on GA. So and that GA act on P1 by translation. So we get infinity, and then, sorry, we get the orbit of 0, say, and then we get infinity, which has a stabilizer group of GA. And this is also going to be something similar to a theta degeneration. I'm going to make this precise. I call it a nearby specialization. In particular, we see that these are both K points. So, and we have in the closure of 0, which corresponds to the orbit, which is P1 minus infinity, we have infinity. So this K point lies in the closure of the orbit of this K point. And this is exactly the same phenomenon that happens here, that here the orbit of 1 is a K point, and the orbit of 1 in its closure is 0. So it is very similar to theta. And let me give you one non-reductive example. This is I think the limit of non-reductiveness that's going to happen in this talk. Well, you could say this is a non-reductive example as well. This is a very bad non-reductive example. So not kind of in the non-reductive GIT.
Just to clarify, maybe you should say that here the topological
moduli
space is not.
Yes, sorry. Yeah. It has a point as topological moduli space. We have to collapse it to K points. In schemes, K points don't specialize to each other. Okay, so final example. Oh, this is some version of non-reductive JIT. So we are starting with what they call that H, a reductive group. So every linear group in character 0 splits as a semi-direct product with a reductive group and a unipotent. And we let that act on. So I'm just going to do affine non-reductive GIT. And really what's necessary to get the topological moduli space or getting a non-reductive moduli space is that the invariance of the whole group, which is of course smaller than the invariance of the reductive part, but they should actually be the same. So this condition ensures that if I quotient out by just the reductive part, well, then I know that I have a good moduli space. Or if I quotient out by the bigger group, then I'm going to get the same invariance. Okay. So this is a good moduli space. And this is going to be a non-reductive moduli space, so it's also topological. And one way to ensure this is that if there exists a one-parameter subgroup which acts on acting with so the weights on the Lie algebra, the dual Lie algebra of the unipotent are strictly positive, and the weights on the ring are semi-positive. So this will ensure that even well, it will ensure this, and it will ensure more. So this is a very, very nice situation. So this is like positively graded non-reductive GIT. And there's lots of nice things happening. I mean, I think almost any theorem for good moduli spaces holds in these kind of settings, except that the existing theorem, which I'm now. But I can't give a good version of the existing theorem for non-reductive. I go to this weaker topological situation. Okay, so let's now state the existence theorem. Perhaps I would like to do it over here. So it's going to be similar, and I'm also going to do the separated version. So, and for simplicity, I'm also going to assume that X itself is post-compact. So otherwise, it's not a big assumption. Oh, sorry, separated. I hope I did write separated last time. So now we're going to have another condition that we did not have before, namely it's locally, the analog of being locally reductive. And I'll call this locally topological. And then we're going to replace theta complete with nearby complete, which one also can split up in nearby closed and nearby separated. And I'm going to give definitions and examples of all these properties. And finally, the corresponding to S complete will be called M separated. So I'll tell you what these are in a moment. But let's perhaps start with this first one. So it says that for every closed point, there exists a local presentation where this has a topological moduli space. And of course we want X to be in the image, and we also want the stabilizer to be the same. And one can do a version of this where one instead require this to be separated, representable, and then ignores this. But perhaps the most important remark here is that this really, it's a kind of a direct, some sort of retranslation of the good moduli space case to the topological in the following sense. So if X is locally reductive, so if we can find these presentations where this really is kind of from affine GIT, then enclosed and n-separated is exactly the same as theta complete, and n-separated and m-separated is exactly S complete. I should also thank Michele for coming up with thinking about this Rydh rotation.
Is there a local structure theorem for it?
So there is no local structure theorem for topological model spaces, and I would say that there's essentially cannot exist. I mean, perhaps I can't make that into a solid statement, but what does exist is local structure theorems in a non-reductive situation. So in a non-reductive situation, the first condition is not a problem. So then you just a condition on how the stabilizer acts on the tangent space. Another funny thing is that the 1, 2, and 3 are stable under infinitesimal thickenings, whereas 0 is not. So it's really 1, 2, 3 is more topological nature than 0. So 0 is a bit, and it's also 0 is also not. Even in a non-reductive situation, you might have a thickening, so that might change the tangent base, and then this condition tangent base might fail. So even for non-reductive, 0 is not stable under thickenings. And also 0 is not stable under affine maps, in contrast to good model space. I don't know if 1, 2, 3 are stable under affine maps. They could be. Okay, so in the remaining time, I would like to go into these conditions. I could perhaps just first mention, since it came up in Jochen's talk, that if we want to do, instead ask for proper, then we can just replace this enclosed by saying that it should satisfy the validity criterion of existence of properties, not uniqueness. So in some sense, in a local reductive situation, if we wanted to find a proper good moduli space, we only have to verify S completeness and existence in the validity criterion of properness. Yeah, I'm going to tell you what enclosed, n-separated, m-separated means right now. Well, let's keep that for instead. But keep this in mind, this finite, till we see the examples, and I will explain why the finites are needed. It has to do with that we are really thinking about potentially algebraic spaces as quotients, and algebraic spaces can, I mean, they are difficult to get hold of just using their underlying space, and by passing to finite covers, we can also pass from an algebraic space to a scheme. That kind of explains why we have to do finite. So, going to all this enclosed, n-separated, and so on. So behind this is first a definition, or a proper definition of this less than equal signs. So, if I have two points, I say that y is a nearby specialization of x, and we write this as x greater than or equal to y, if I pick for some or for every representative, so I pick some representative of x, I can find as a specialization, and let me call this now y prime, and this takes place in the base change of the stack to this field k. And I want that to lie above my originally x and y. So if my stack would be defined over a field and I would start with a k point, I'm just saying that y is a specialization of x. So this is exactly what happens here. But here I first need to base change to capital K, so that otherwise, this is a specialization of this, but after base change to capital K, I only have this as my specialization. So the less than equal signs here are nearby specializations. And the point is that for schemes or for algebraic spaces or for stacks with finite stabilizers, so there are no non-trivial nearby specializations.
So what is n? N is a number? Or is
N is nearby. So you should think of somehow that these points are closer together in the stack. I mean, any map to scheme will have to identify them. So this is also a nearby specialization. And having nearby specialization, we can also we get an equivalence relation which I could call nearby equivalent by taking zigzags of nearby specializations, and this gives equivalence classes, which I can denote by bracketed. And now we can come to the conditions. I'm going to start with n separated. And as you'll see, these are very familiar conditions. But what's perhaps less familiar is that just as in the definition of topological moduli spaces, I have to impose these conditions not just on X, but on every finite map to X. So this is what makes these conditions in principle impossible to verify in any moduli situation. So the relative theory of properness is very nice, because if I just take a DVR and I apply it to my moduli stack, I have a family of something and I know exactly how to do it. Here, I'm going to pose a condition not on X, but on a finite thing on X. It has to be modular. So it's not just going to level structures, it could be anything. It doesn't have to be flat and so on. So it's terrible for moduli purposes. But one could imagine that one could find a relative thing that easily implies this. This is a super easy. And this is nothing deep at all. It's very almost immediate, as you'll see. The condition. So for everything finite over X, every nearby equivalence class of X prime has a unique close point, or let's say n close points. So this is what I call special points. So these are really you should think of this as the polystable points, right? So these are the unique closed points that would exist in the fibers if I had a moduli space. So the 0 little k and 0 big K are the unique closed points in the two n classes that exist in that example. So and
why are you saying n closed? What does that mean?
well, so it doesn't have any further n specifications. It's a minimal under no further n specifications. So if you would take the induced topological space on that Kunst class, it will be closed. So I'm going to illustrate this with non-examples that exactly fail this condition but satisfy the other conditions. So here the canonical example would be to take P1 mod GM. So it has 3 points. It has the orbit of 1, and it has the orbit of, well, the fixed point 0 and the fixed point infinity, and these are both nearby specification of the open orbit 1. So this has two enclosed points in this single equivalence class. A more refined counterexample is to consider the nodal cubic mod GM. So I mean this has exactly two orbits. It has I mean, I've now identified 0 infinity, so it has only 1 point. It has stabilizer GM, and then it has the open orbit. So this now has a unique n-closed point. It has a unique closed point. But it has this finite map from P1. So, and since we require this for finite maps, we see it failing. So the thing about validity criterion is that if you have a validity criterion for this, it automatically implies the validity criteria here. So validity criteria automatically kind of are stable on the finite things. But when we just look on the topological side, we don't see this. So we really have to go to finite. But as I said, in a modular context, it will be hopeless to verify. But I guess in principle one could hope to use it for doing some non-modular complexifications or similar stuff. Okay, then we come to the next condition.
I have a question. So
Yes.
you said somehow like these 1, 2, and 3 are you phrase as something valuable and something kind of local. I don't know, did I hear you say that?
Yeah, so here there are some valuative things, right? Here I can't do anything valuative. These are non-valuative.
1, 2, 3.
Yeah, all these three are not. So 3 is a bit. 3 is towards being valuative, but it's not. It's not in terms of any regular stacks or codimension to filling and so on.
In the second non-example, what of the defining? So this is not a topological space. Which of the definitions does it fail?
It fails and separated. So here I have a unique close point, but there is this.
Those were conditions in the fractions definition.
But n separated requires for every finite map they should have unique n close point.
So the question is from the definition.
Yeah, from the definition. That's part of the theorem, but from the original definition, where did this guy fail?
You mean why if I would do the map to a point, why this is not a topological model space?
Yeah.
So it also in definition, I said that for any finite cover, I take this time factorization, it should have a unique close point.
What's that sign?
And I take this one, it has the same sign factorization, it doesn't change because it's birational. So I'm not adding any invariance when I pass this, and then I get two close points. So the finiteness in the definition of topological model space is kind of reflected in the finiteness here. Now we have the n closed. And again, it's going to be for every finite. For every finite map, and for every diagram. And I'm also going to, again, not use, so I think Michael used the one, 0 specialized the one, I'm going to do the opposite, of course. And I'm also going to draw my specification to the left and not the right. So this is just a regular specialization. This is a nearby specialization, and for every such diagram, I want that there should exist. I can at least use the red color, as Michaela did. There should exist, or if I want to be even weaker, just some nearby equivalent point that this specializes to. Typically, this will be a specialization, nearby specialization. So let me again give you non-examples. The canonical example here is take a to minus 0, mod out by GM. So here the weights are 0 and 1. So the picture is that on the when y equals 0, I have a GM stabilizer. When y is not equal to 0, I don't have any stabilizer, and all these points are have this nearby specialization to y equals 0. But what happens here is that if I pick a y1 here and y0 here, and then I take x1 to be this point, then it has nothing that this specializes to in the same n equivalence class. So one could hope that this will be this is not a topological model space for the reason of the theorem. There's also you can soup this up to also make an example where you need to use a finite to see this happening. You again need to do the finite, and then finally we have M separated, and it's again for all finite. And what I'm going to do now is I'm going to try to force different lifts of same violation ring to be equal on the moduli space. So I think of this as the moduli space being separated. And the diagram that I'm going to have for all. And now I'm really using DVRs here. So here I was just using any specialization, not necessarily coming from any violation ring. Here I'm using DVRs or violation rings, if you like. And I'm going to draw this exactly the same diagram as we had for SD bar. I think it's even above me. So I'm taking two specializations in the stack coming from maps from spec R, and I want them to both. I want them to be equivalent. Okay, let me phrase this properly. For all F1, F2, or let's say FG, spec R to the stack X, if the generic points are equivalent or equal as points, then the special points are n-equivalent. So I want them to be n-equivalent. In the SD bar, this happens because they're both specialized to some common points. So what's going to happen if I have now a lift? So I'm starting with two spec R's here, and then they're going to be n-equivalent. When I map it down to the moduli space, they're going to be identified. So saying that the moduli space is separated. But I'm going to need this finite again.
So they have clear maps for X prime?
Yes. This diagram happens. So non-examples. So here there are kind of two different kinds of non-examples. Should perhaps bring up my notes so I remember the examples. Right, so the first is even not a stack. there are these badly non-separated algebraic spaces that they look very much like they would be just affine line, but I can put in here something that locally looks like a null singularity, but then kind of goes back to the line. So if I'm just looking at points of this space, I don't see that it's non-separated. But there is here, I can normalize this, and if I normalize this, I get exactly the non-separated line. And here, so now I have these two spec R that are not nearby equivalent. So this is just a pinching of the non-separated affine line. It's an algebraic space when you pinch those 2 points. Another non-example, I mean, you can do a similar one as this one. This bug guide covers. So it's a very similar example. It comes from taking a ramified cover, and then you take a non-separated. So you take 2 points of the ramified covering, and then you identify the 2 points here and the 2 branches, and then you get this bug guide cover. And again, from here you can't see that it looks separated, but when you pass this finite 2-to-1 covering, then you see that it's non-separated. And there's also, perhaps I should mention this is a third example of this category. Of a more stacky kind, is that you might have a stack with non-finite inertia. So you have let's say a Z mod 2 stabilizer except at a point. Again, this looks separated, but then you pass the 2-to-1 covering, and then you see that. So here I have the action that interchanges just the two origins, and I get this stack. So this is not separated, this looks separated from a topological point of view. Yes.
So by separating topological moduli space, you mean you actually meant the map pi itself from X, the stack to the topological space?
Well, I usually refer to the algebraic space as the topological moduli space, but sometimes perhaps the map.
So is the topological moduli space what is separated over the base?
Oh,
Or is
yes,
the map
yes.
that is
No, it's not the map. No, so it's that it's being separated. It really means that this is. So as you can see, there's these conditions. All these conditions are really global on the stack. It does not refer to any base, and similarly nearby space, it does not depend on which scheme you consider it over. If you would consider a stack, that would be a different thing. But if you consider something over a scheme, none of these conditions really care. But you could for M separated, you could want your spec R to live over the base, and then you would get separated over the base. So that's fine. Yeah, so I think I started a minute late, but it's not time enough to say anything about the proof. But I could say one thing. Let me say morally. So if I have my map here, it's going to be such a fibers or nearby equivalence classes. So that they have to be union of those, but I want exactly one for each. And then this being enclosed is roughly saying that pi is closed. You can make a precise statement, but it's you don't get universally closed and so on, but it's roughly nearby closed is saying that this map is closed. That X is nearby separated let me say plus epsilon, is saying that this really tries to be separated as well. It's not separated, but it's kind of getting towards that unique close points and so on. And this being M separated is roughly saying that the moduli space is separated. But again, it's actually saying a bit more, and this has to do with this unpunctured inertia stuff that appears if you want to do non-separate things, and I don't know exactly what this right condition is in the topological situation. But what this says is that really these conditions, they are trying to make this proper, that's the first two, and the third one is trying to make this separated. But you also need this locally to really make it into a scheme or an algebraic space. Okay, thanks.
Other questions for David? Yes.
So, assume locally, you know that the structure is continuous like X mod H.
Yep.
And is there anything like valuation criteria which can guarantee that they include?
No, I don't even know a good validity criteria for BG. So the problem is that this S completeness, it really forces G to be reductive. So whenever it doesn't a priori doesn't look like that because this has to do with specializations and so on. But if you map these kind of diagrams into BG, it actually forces G to be reductive. So what I do know is that it's enough to consider in a non-reductive situation to consider just certain diagrams of theta minus 0 and certain diagrams of ST bar minus 0 to arrange this. But I can't pinpoint which maps from theta minus 0 and ST bar minus 0 are necessary. So if you take all diagrams, then you have to be reductive. But the test case is, of course, just BG or spec A mod G, and try to understand what kind of.
So the N stands for nearby, and the M stands for moduli?
Yeah.
But if you drop condition 3, the theorem, and just try to ask if there exists any moduli space, then it's...
You can replace 3 by unpunctured, but then you don't get if and only if, then it's sufficient. You can also replace just by horizontally unpunctured, and then you get something that's also sufficient. If you do unpunctured, it's not necessary. There are examples which has punctured inertia, which are topological moduli spaces. So I don't know the correct. You can put in very artificial conditions, like I mean, what you want 3 to do for you is that not only you have the same stabilizer at W, but you also have the same stabilizer in the neighborhood. So if you require that, then it's fine.
Maybe you mentioned
Okay.
this. Sorry. Maybe you mentioned this, but do you then have universality?
Yes, I did not mention it. Sorry. Yes, topological moduli spaces are universal to algebraic spaces. You have finite generation. If you have finite type or Noetherian base, then your moduli space is finite type. Preservation of coherent things. You have Luna fundamental lemma. You don't have things like coherent completeness in general. You don't have local structures, I think, in general, and so on. Yeah. There was some question. Yeah, Karim.
Yeah, in the remark after the theorem, so I can see if your theta and S complete, why the others hold, but in the other direction, is there like some easy, intuitive way why?
Yeah, so it's pretty easy. So if, as you said, if this holds, I mean, you start with a diagram, you just you show that it can be realized by theta, and then you fill it up. But for converse, you really use local reductive. So you're starting with something which is, I think if you know that it is satisfies this, let's say the node satisfies this, then you want to see that it satisfies theta completeness. Then I'm going to start with a diagram from a theta like this. Then I'm first filling it up with an n, which means I just have something here. And separated will be that I can make this a neighbor specification. Then I take the local structure at this point. and then I try to move this diagram over the local structure. But I really need to use this finiteness that it's. So I'm going to use that it's also finite things. So what I'm going to do is I'm going to take a series domain theorem factorization of this map and use that it holds also for the finite thing.
So the good moduli here is this descent for vector bundles. So when the vector bundle descends to the good moduli space, there's something like, so maybe characteristic 0.
I would say it's false for adequate. Okay, false characteristic, and it's I mean there's a version of Luna fundamental for smooth maps which is very close connected to the set of vector bundles, and that's also false. And I think that is also false for the non-reductive situation, I think. So I think it's also false for the set of vector bundles in the non-reductive. I mean, in many cases, the non-reductive situation is much better than an adequate situation, but I think for this, I think it's just false. But I would have to do an example and see if.
So for this enclosed and separated and unseparated, you need to check for all x prime finite. Is it possible that, could you speculate a little bit, is it possible to restrict this class if you assume something about x itself?
Yeah, I mean, even if you're normal or smooth, I mean, I think you still would have to do finite covers. I mean, I think, this is a smooth example. For example, you need to do a finite detail. There's example you have to do it also at closed substacks. So I mean, you can't do it like flat maps; it would not be enough. So I think it's pretty hopeless to limit that to anything verifiable. But I think it's somehow, I mean, the topology at least it gives you a hint, like in Michele's talk, really what you have to do. I mean, filling is these diagrams without having to worry about mapping a theta is a bit morally simpler. And then we would like to have a relative thing, and then any relative thing would automatically be stable on a finite.
Johan, do you have a question?
Just speak it was, I mean, you explained why this punctured version of theta doesn't
satisfy the criteria, but is it directly, is there a short argument why the topological modular space condition fails?
Right, yeah, it's not universally closed.
What base change do I have to do?
No, this itself mapping to A1 is not universally closed.
Ah, yeah, sorry.
Yeah, so
Sorry,
yeah.
yes.
So for this example, you don't need to do a finite, but you can make a complicated example where you need to do a finite. You kind of, if you do the nodal thing and you glue in, like, yeah.
Thank you.
But all these examples just fail one of these conditions, so they're kind of sharp in that sense.
There are no further questions. Let's thank David again.